All right, in section 4.5, we're looking at finding extrema on a closed interval. Now, we've certainly found extrema, maxes and mins on open intervals, finding relative max, relative mins, where we're changing from increasing to decreasing or vice versa. But we're going to use this idea of doing it on a closed interval to solve some of our future word problems that will come up in future sections. So a closed interval is when you have an interval, a to b, including a to b, and then all the numbers in between. So we have a theorem that is sometimes called the extreme value theorem. And the extreme value theorem states this. In any closed interval, if the function f is continuous, it has a maximum and a minimum value in that interval. So if we think about what this means, let's go ahead and draw a little picture. So let's say I have 2 points A and B. Just for convenience sake, I'll make A here and B here. So let's say my graph just kind of winds along. Let's say it's got a closed dot here, because again, it is a closed interval. It doesn't go on forever. And let's say it's continuous. There's no gaps or holes, and eventually it stops down here. Now in this case, the maximum value, the biggest y value in this whole interval would be here. This is my absolute max in that interval. And then my absolute min is going to be down here at this endpoint. And so these maxes and mins in this interval always happen at these critical numbers, at these, old thing we used to call relative max or mins, or at the endpoints. So really all we're trying to do is we're trying to figure out, does the highest value happen at the endpoints or at the critical numbers of the first derivative? So no real new calculus here. We're just kind of finding the critical numbers and then plugging them into the function to see which one's the biggest, which one's the smallest. So let's look at a relatively easy example here. We have a quadratic. So this is negative x squared plus 4x plus 5 on the interval negative 1 to 5. Now, if I wanted to graph this, I certainly could. This is going to be a parabola that is upside down. So we have negative 1 and 5. I could plug in and see what these are and try to see what this graph looks like. And so Desmos is telling me the graph looks something like this. So it's at 0 there and it's at 0 there, and it kind of does something like this. So just kind of eyeballing it, I would say the minimums are at both of these points, and then the maximum is somewhere up here. So first thing I'll do is I'll find my first derivative. So f prime of x is going to equal negative 2x plus 4. And then so for my critical numbers, I'll find when that equals 0. And again, this is just a linear equation, so that makes it really, really easy. So I'll subtract 4. So negative 2x equals negative 4. So x equals 2. So my guess is that value is going to be 2. That's going to be the biggest one, because remember, the critical values, the max and mins, have to happen at these critical numbers or at the endpoints. So what we will do in general is we will plug in the endpoints into the function, the original function, so f of negative 1 and f of 5, and then we'll plug in f of 2. So the extreme value theorem says one or multiple of these will be the biggest value, and one or multiple of these will be the smallest value. And sometimes there'll be some in between. It just depends on the function. So when I plug these in, f of negative 1 is 0, f of 5 is 0, and f of 2 is 9. And I'm just plugging that into my original equation. And so these two are going to be considered minimum values, and this is going to be our maximum value. Now, if there was a third or fourth point that was somewhere in between, it just would be neither. And that could happen as if you have a graph, it does something like this. There'll be some in between that aren't maxes or mins. So let's look at another example here. So this one has a fourth degree equation. And so I want to find the max and min. So if I graph it, find the derivative, f prime of x is going to be equal x cubed because the 4 cancels. And this is going to be minus 4/3 x on the interval 0 to 1. So if I pull some of these values out, I can pull an x out for sure. So I get x, and then I get x squared minus 4/3. And so this is what I want to set equal to 0. So if I set this equal to 0, part of it is going to be good. That's this first part. So x equals 0 is a critical number. And my other critical number is going to be when I take x squared minus 4/3 and set it equal to 0. So x squared is going to equal 4/3. So when I take the square root, x is going to equal plus or minus square root of 4/3. Now, there are 3 critical numbers, but I'm going to claim I'm only going to choose 2. I'm definitely going to use 0 because that's in my closed interval, because I'm looking for only points between 0 and 1. But I'm not going to worry about the negative one, because negative square root of 4/3, whatever decimal that turns out to be, is going to be less than 0. Now for the positive square root of 4/3, that's about 1.15 according to Siri. So that is also going to be outside of our interval, because remember, we're only looking at points of 0 and 1. So I only have to look at critical numbers that are in my interval, which in this case is 0, and then the 2 endpoints, which also include 0. So really all I'm going to check is I'm going to check f of 0 and f of 1. So if I plug in 0, I get 0. And if I plug in 1 to the original, I get 1/4 minus 2/3. Where if I get my common denominators, that's going to be 3/12 minus 8/12, which is negative 5/12. So my max is going to happen at 0, and my minimum value on this closed interval is going to happen at 1. So when I graph this, it kind of agrees with what we see. Because what I see, I mean, there's lots of the graph, and it kind of does something like this and all, but all I really care about is the interval from 0 to 1, which is going to be here. And then at 1, it's down here doing some kind of curve like this. And so the max is at 0 and the min is at negative 5/12. All the rest of the graph I don't care about. We're only doing it on these closed intervals, which makes our life quite a bit easier. All right, let's go ahead and look at another one. So this one, again, is a polynomial. So a lot of these are polynomials. We'll get to a trigonometric one here in a little bit. You could have rational ones, all those kind of good things. So this one, we're looking for f prime of x of this cubic. So I'll get 7x squared plus 4x minus 3 is my derivative. So when I'm setting it equal to 0, 7x squared plus 4x minus 3. Now we have a quadratic, so most quadratics will factor, but if not, you could obviously use quadratic formula, but this one should factor if I fiddle with it. So we get 7x and x, I get plus 1 minus 3, so there's my 7x minus 3x, so there's my 4x. And again, you can factor a quadratic formula however works best for you. So then I'll set my two factors equal to 0 for my derivative. And so I'll get x equals 3/7 and x equal negative 1. Now, our interval here is from negative 4 to 9, so both of these numbers are in my interval. So when I'm finding the max and min values, I'll include the endpoints, f of negative 4, f of 9, but I'll also include f of 3/7 and f of negative 1. So of these 4 values, one should be the max and one should be the min. And again, some could be tied, but essentially there'd be one biggest value and one smallest value. All right, so I'm just going to put these in my calculator. You put it in Desmos, wherever you want. So for f of negative 4, I'm getting negative 104 and 1/3, negative 104.33333333. For 9, I'm getting 18 37, so a really big number. Now 3/7, not surprisingly, is some odd decimal, 0.2653, blah, blah, blah. And then f of -1 is going to give me 3.663 2/3. So our maximum point is going to be here. Obviously, it's 1800, and the min is going to be at -104 1/3. So that happens at the end points. Not surprising, if you look at a sketch of the graph, you're going to have this point way down here at -4. It's going to kind of come up here and turns at -1. Comes over to some weird point over here, which we now know is 3/7, and then goes way up to like 1800. So this would be what our interval would look like. So not really surprising that the biggest is at that right end point of 9, and the smallest is at that left end point of -1. All right, let's look at one more. This one's a pretty tricky one. We're looking at -2 cosine x plus 2 sine squared x on the interval 0 to 2 pi. This is gonna stretch our knowledge of trigonometry, just finding the derivative and being able to solve it. So first thing I'll do is I will take the derivative. So the derivative of cosine is negative sine, so the derivative of -2 cosine x would be 2 sine x. That's not my problem. My problem's going to come in this next part, because I actually have a chain rule problem. If you remember the chain rule, because this is essentially 2 times the sine x squared, so we have an outer function of something squared, so my derivative is going to be 4 times that something to 1 less power, because I'm bringing that down, 1 less power. But remember, we leave the exact same thing in there, which is sine x, but then the chain rule says I have to multiply by the derivative of that inside. So bringing back the chain rule is something we haven't done in a little while, so that's kind of a nice way to do this problem. So this derivative turns out to be 2 sine x plus 4 sine x cosine x. So I want to find my critical values where this is 0, but the nice thing is, if you notice, they both have a sine x. So I can just go ahead and take out my sine x, and I'm left with 2 plus 4 cosine x. So my two factors I'm trying to solve for my critical numbers will be, where is sine x equal to 0? And where is 2 plus 4 cosine x equal to 0? But with some pretty easy algebraic manipulations, namely subtracting 2 and dividing by 4, this is the same as asking, where is cosine equal to -1/2? So the easiest way now is to look at unit circle. Remember our unit circle. This is obviously not a complete unit circle. 0, 1 up here, 0, -1. So where sine x is 0, sine is the y coordinate. So sine is 0 here and here. So this is going to be at values 0 and pi and 2 pi. And again, any unit circle will tell you this. Cosine x equal -1/2 will be a little trickier, because we have to figure out where on the unit circle is cosine equal to -1/2. It should be here and here if you just look at any unit circle. It should be at these 2 points, because this point is -1/2 comma radical 3/2. And this point is -1/2 negative radical 3/2. So these angles are 2 pi over 3 and 4 pi over 3. So this part of the graph is going to give me those two critical values. So now I have to figure out all of these functional values, all 5. You'll notice the 2 endpoints of the interval are 0 and 2 pi. Those are already included. So I'm really going to find f of 0, f of 2 pi, f of pi, f of 2 pi over 3, and f of 4 pi over 3. And then when we do this, and if you look at the graph, it should show that these are all some kind of turning points, but there'll only be one maximum value and one minimum value. So if I find these values, f of 0 is -2, f of 2 pi is -2, f of pi is 2, f of 2 pi over 3 is 2.5, and f of 4 pi over 3 is 2.5. Now, I literally just plug those into a calculator, so you could certainly do that. And if you look at the graph, it's a really cool graph. So I really encourage you to sketch it and see what it looks like. So a quick sketch of it's going to say, so we're at 0, -2 down here. And then it goes to 2 pi over 3, kind of concave up a little bit to there. And then it does one of these guys. So this point is going to be pi. This is going to be 2 pi over 3 because I know it's these critical numbers. Then here at 4 pi over 3, it's going to be at its max. And then it's going to get dipped down to here at 2 pi. So it's kind of like a fancy m. And the cool thing is, since it is a sinusoidal function, it does repeat itself. So if you look at this, it looks like a bunch of these things over and over and over again. So I would encourage you to graph this on Desmos just to get a quick peek what it looks like. But for this problem, obviously the min is going to be at -2, which occurs at 2 different places. And the max is going to be at these 2 places. And that's fine, because when you see a word problem, there could be 2 solutions that give you the biggest or the smallest amount. Because our word problems we're going to be talking about, that's what we're going to be trying to do. We're going to try to maximize and minimize functions, make it the biggest or make it the smallest. So again, check your endpoints, check your critical values, and that will give you your minimum max value in your closed interval. If you have any questions about this, obviously, please let me know.